Alright, last problem on homework 1, which is Maxwell's relationships. It says, in class, so if you're not part of my class, this won't make any sense, but I will show you what you need to be seen. In class, we derived a relationship for self-healing polymers. Assume two self-healing polymers have the properties of gold and air respectively. Which would self-heal better and why? Now, in the case of those I'm grading this homework for, you can just kind of end with the relationship, that's fine. But for those folks at home, or if you want more practice, let's start from where we started. Okay, for self-healing polymers, we came up with this relationship that dVdH at constant P. Okay? And so now we go through our questions. Okay, do we have a funky function? No. Do we have an HTC in the constants place? Do we have an HTC in the dx place? Yes, we do. Is it on top? No, it's not. So I need to inverse this, but I just need to remember to inverse it when we're all said and done. Okay? And then I plug it in. Now, why don't I plug it in now? Because you guys have that damnedest tendency, when you after you plug it in, to do this snotty nonsense. Can you do that? No! Don't! Naughty! So, let's inverse it first. Okay, so dH, dV at constant P. What do I do when I see a HTC in the dx place? I plug it in. Okay, so now I do TdS dV at constant P plus BdP dV at constant P. Oh, well, hey, that's equal to 0 because if I keep P constant, I'm trying to change it. Well, it's 0. ds dV at constant P, and if you've been watching the other videos, I think, oh my gosh, that's the same exact thing I've been putting in all this other time, right? No? No, it is slightly different. Okay, so I have a well, let me go through the questions. Do I have an HTC still in the dx place? No. Do I have an S in the constants place? No. Do I have a ds? Yes. Do I have a Maxwell's relationship? I do. Does it help me? No. Why doesn't it help me? Because I put S in the back in the constants place. Okay. And so I need to use what in this case? The chain rule. Okay. And so again, T ds d something at constant P times d something dB at constant P. And what's the something? Well, it's a nose principle, and you get to pick it, and I like to pick T. T, okay. And now I just, and I have ds dt at constant P, so I can just plug that straight up. So that is Cp over T, oh, and there's a T there, times dt over dV at constant P. My nose cancel out. But I need to inverse this again to get it back. So my dVdH at constant P is actually equal to 1 over Cp times dV dt at constant P. Okay, and those units do work out. Okay, so my units are good, at this point at least. So I want measurables, properties, or equation of states. Do I have an equation of state that I can use that compares both gold and air? No, I can't. Do I know how volume changes with temperature for gold versus air? Possibly. Well, let's just do it that way then. Okay. Because heat capacity. Do I know how heat capacity... Now, for those at home, now we did simplify this out to become, alpha over... beta over rho Cp. Okay, so we did do that. But we don't need to do it in this case, actually. We don't have to, anyways. The question asks, which would self-heal better? Because in class, what we decided is we want the volume to change as little as possible. That's what the research has established. We want volume to change as little as possible. So that means we want dV to be as small as possible, which means we want this relationship to be as small as possible. Now, in this case, if dV dH constant P is going to be as small as possible, that means we want beta to be what? Big or small? We want rho to be what? Big or small? We want Cp to be what? Big or small? We want beta to be small. We want rho and Cp to be big. Because divided by a big makes this a small. Okay. So, but I have to look at, so we can look at this in kind of a couple ways. Okay. So let's look at it this way first. Heat capacity. What do I know about the heat capacity of gold versus air? Do I have to look it up? Not really. I mean, maybe I do, but I don't know. They could be close. I mean, I'm sure it's a lot harder to heat up metal than it is just air. But okay, so maybe air. Okay, so maybe if I have, what I want to do is like, okay, I have air and I have gold. Okay, and then I have Cp, I have rho, and then I have beta, and then I have just dV dt over constant P in general. Okay, so let's put an X about which one is bigger, or I'll put like a lot of X's if it's really big. Okay, so maybe this one is a little bit bigger. Okay, density. Well, we know that this is like just enormously more dense. Okay, just orders of magnitude. I mean, it's like 19 kilograms per mole, not 19 grams per mole. I mean, it's humongous. Okay. Beta, heat capacity. Well, beta is thermal expansion coefficient. Okay, so thermal expansion coefficient, what is that? Well, it is, it's really this. How much does the volume change if I change the temperature? Okay. If I heat up gold, what happens? Does it expand? Or does it contract? It does expand. Same thing with air. But I would say that air is probably going to expand more than gold. How much is it going to expand? I don't know. But if I really think about it, well, that one's going to cancel out that one. And it's really the density. I mean, yes, this one could be a lot bigger than this one. Or this one could be, the beta of air could just be a lot bigger than the beta of gold. But is it the same orders of magnitude bigger when you look, this is like 4 orders of magnitude kind of thing. Is it 4 orders of magnitude higher in terms of beta? Probably not. And so it's really the density that makes the deciding factor. Because gold is so much more dense than air, that's going to be the deciding factor. Everything else is just kind of inconsequential. Now what I have to say is, okay, this one's bigger, which makes this big or small. It makes this small, which makes small, which is a good thing. So gold is your better self-healer. Why? Because the density is orders of magnitude higher. So this is a numeracy thing again. Getting to this point, that's Maxwell's relationships. That's straightforward. That's important, but not that important. What's important about Maxwell's relationships is that second word, relationships. This relationship tells us, how does volume change with enthalpy? How does volume change when I input a large amount of energy, aka a bullet, into this system? And what's going to change the volume? Well, what's going to change the volume? Beta's going to change the volume, density's going to change the volume, and the heat capacity is going to change the volume in this system. And I have to look at that relationship and say, oh, well, which one is going to make it change more? With the same amount of energy input, they are all going to affect it. But the one that it's going to affect it the most in this case is density. Now, in the case of the polymers that were actually presented in class, the densities are actually really similar. It's the other two that have a huge difference. The heat capacity and the thermal expansion coefficient are drastically different between the polymers, and that's the dictating factor, because the densities are so close. But in this case, it's the densities, not the other. All right, but I don't need numbers. I just need to look at the relationship and know that coal is, well, very dense.